The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
So the title of my talk today is going to be the innovative design of bridge columns using high-performance materials. I'm going to present some of the research we have done about a year ago, and we're still planning to continue along these lines, but we still need to plan for that. I need to acknowledge the students, obviously, who were working on this project. They have been doing the heavy lifting, Farshid and Sirwan, and then there were several undergrad students who also helped them. I would like to acknowledge the support of Professors Kainuma and Omori and Professor Eki there. They helped a lot on the material side of the research, and I would like to also acknowledge the sponsors, National Science Foundation and the NASA Johnson Space Center. They have provided funding for this research. So this is what I'm going to go through today. The introduction, I'm going to tell you about the motivation for this research. I'm going to talk about the high-performance materials. You have already heard enough about those. I'm going to basically be talking about fiber-reinforced concrete, a special type of fiber-reinforced concrete and shape memory alloys. Then I'm going to talk about the design and testing of these, what we call the innovative columns. I'm going to tell you why we call them innovative. You might think otherwise. But then I'll present some results and discussion and some conclusions and future plans. So we all hear about this deteriorating infrastructure in the United States. This report card for America's infrastructure prepared by the American Society of Civil Engineers tells us that the overall grade of the infrastructure is a D+ on a scale from A to F. So in this research, we are particularly focusing on the bridges, and the rating for bridges is the C+. And if we want to dig in a little bit into the numbers, I'm sure most of you have seen these before, but just to remind you, there are about 600,000 bridges in the United States, and about 1/4 of these bridges are either functionally obsolete or they're structurally deficient. So functionally obsolete means that they do not meet the current codes and standards, and structurally deficient means that they need significant maintenance, repair, or in even some cases replacement. And the average age of a U.S. bridge is 42 years, which means that since they are designed for about 50 years service life, they are coming to the end of their service life. We will see a lot of bridges being replaced, hopefully, in the near future. To eliminate the backlog, we need to spend about $20 billion every year, and we are currently doing about $13 billion. Among many other concerns, obviously, for our infrastructure, particularly for bridges, the two main concerns are the deterioration and aging-induced deterioration and earthquakes, and I'm going to tell you why. One of the main deterioration mechanisms that we see in reinforced concrete structures is obviously the corrosion. Corrosion is maybe more of a concern for bridge decks and pavements, but it's also a concern for these structural elements of the bridges like the piers and the band caps. You can see here an extensively corroded bridge pier, bridge column along the entire length, and we see significant corrosion damage in the band caps as well. The second concern is obviously earthquakes. Bassam and others have discussed this quite in detail. I think Bassam was using similar pictures. These are from the Northridge earthquake. We see in some cases very brittle damage of these bridge piers. Now, if we look at these two things, I would say the main difference from what you have already seen in the past two presentations is that in this research we are trying to address two hazards. One hazard is the earthquake hazard, and the other hazard is the aging. So on the left here, what we have then is a distribution of the structurally deficient and functionally obsolete bridges in the United States. So the warmer colors mean that there are more bridges in that county that are structurally deficient or functionally obsolete. And this map on the right, you have seen it before, is the seismic intensity map for the United States. And this is an old map, but it does the job. So if you look at these warmer colors, unfortunately, the warmer colors are on top of each other. If we exclude like Texas, where I live, the Michigan and Florida, if you look at the warmer colors here, there are warmer colors there, and on the West Coast, obviously, there is a lot of earthquake potential, and we have a lot of deficient bridges on the West Coast, which is not a really good match. Now, we really don't understand, unfortunately, the impact of a significant earthquake in the future on the bridge infrastructure. What we have seen in Christchurch, for instance, is a good example. They thought that they knew what could happen in the case of an earthquake, a major earthquake, but they were not expecting the damage of economic loss in Christchurch. So we really can do all sorts of predictions, but we really don't understand what might the next major earthquake bring us. We came up with this new column concept. Again, this is not for repair. This is for new bridges, so this is for new construction. And there's a prefabricated reinforced ECC tube. ECC is the same ECC that you have seen in Dr. Tazar's presentation. This is basically a tube that includes the longitudinal reinforcement, so the longitudinal reinforcement is already inside the tube, and then we also have the transverse reinforcement in the tube. Transverse reinforcement, there's still the question whether we need it or not, because ECC provides some internal confinement already, but this is something that we'll study in the future, whether we can remove that spiral reinforcement, make the construction easier and cheaper. Then there are these debonded SMAs. I'll call them SEAs rather than SMAs in this presentation because they're in superelastic mode, and they're a different type. They are not nickel-titanium alloys, but they are copper-based alloys. The reason why we're using copper-based alloys, although nickel-titanium is more robust, is because nickel-titanium alloys are very expensive. So I really wanted to ask Mustafa after his presentation how much he paid for those number 10 diameter nickel-titanium bars, but I don't want to hear the answer. Probably it's in the tens of thousands, probably. The reason we wanted to use the copper-based because they're significantly cheaper than the nickel-titanium alloys, but obviously they are still in the development stage and they are not as robust. So there's a lot of variability in the properties of these copper SEAs. So this is the column. You take the prefabricated column, you put it in the foundation. So you pour cast-in-place concrete into the foundation. You can pour the concrete if you wanted to. What we did, we poured concrete also inside the tube. But if you want to not do that, you can try that too, which we will do in the future. And then you can pour the band cap as well afterwards. So what is the advantage of this concept? So if we think about durability, if there's chloride attack on the column, this ECC has much higher crack tightness. Even in cracked state, it has much lower permeability compared to a conventional concrete. And the second thing is, in this combined hazard situation, is the earthquakes. So when there's an earthquake, hopefully these superelastic alloys in the plastic hinge region will make this column behave like this flag-shaped response with some energy absorption but no permanent drift, so that you can still use the bridge immediately after an earthquake. Now, is this the best solution? Is this the only solution? Of course not. I mean, there are many other alternatives, and you might have heard some other presentations in this convention or elsewhere. And there are concrete-filled steel tubes, there are concrete-filled FRP tubes. There's repair strengthening, such as what Dr. Andreu has presented with FRP composites or other materials. And there are post-tensioned, unbonded, precast segmental columns with or without energy-dissipating devices. So this is one of the many solutions that we can come up with, and then we can do all sorts of assessments and comparisons of these different alternatives. So a few words on ECC. ECC is a special class of fiber-reinforced concrete. So if you look at the behavior of conventional concrete in tension, obviously all cementitious materials are pretty good in compression. So if you apply compressive loads, there's usually not much of a concern. The main concern is in the tensile loading. So if you take concrete, if you apply tensile loading, this is what you're going to get. You will see a single localized crack with a brittle failure. If you look at a conventional fiber-reinforced concrete, after the peak, you will see some softening, which is due to these multiple cracks, crack distribution, but still there is not much of a crack distribution and there is still a localized crack. And in the case of ECC, there is a significant strain hardening region, this region, which causes this abundant multiple fine cracks. And after that, you always again see a localization with a single large crack. But this really happens at a very large strain, and that very large strain depends on who you ask, really, and then how you prepare the material. Again, the advantage is in uncracked state, it has lower permeability. And even in cracked state, it has much lower permeability because you directly expose the rebar in most cases in the case of conventional concrete. Now, there are many features that ECC has been proven to be superior to concrete, conventional concrete. In this research, we are going to capitalize on the low permeability, the crack tightness, and the spalling resistance. So we are saying crack tightness. We are not really too much interested in the tensile strain capacity, although it's related to the crack tightness, but our main focus is on the crack tightness. This you have already seen. Mustafa has shown, I think, the superelastic behavior, and Bassem showed the superelastic and the shape memory behavior. Let me add one more here, which is this behavior, which is like the ordinary plastic deformation. If the temperature is really above this, what we call the martensite Desets temperature, And this is, I don't know anybody using SMAs in that region, but in this research, again, similar to what Dr. Tazar has presented, we are using in the superelastic region, and that's why we call them actually superelastic alloys. Now, these are different alloy compositions for shape memory alloys. The most commonly known and used system is the nickel-titanium. Dr. Andraves is using nickel-titanium niobium, I think, which is because of the hysteresis temperature hysteresis, which is larger in that case. And there are a couple of versions which we don't use. They are quite brittle. There are some notes here, the reasons why you don't use them. And there are some gold and silver ones. Obviously, they are too expensive. Even if they're not expensive, they are toxic. There are nickel-aluminum ones. They are brittle. There are some iron-based ones. They're either too expensive or they only show a small recovery. And then the alloy that we are using for this research is this copper aluminum manganese alloy, which we call the present alloy, and considerably cheaper than the nickel titanium counterpart. So because this material is not really very well characterized still, we have done some testing on this material. I'm going to present some of the results here. There are more here in this paper if you're interested, if you can go back and look at this paper. What we have done here is we subjected these bars with different diameters to increasing strain rates. These are cyclic loading in tension, and these are the corresponding strain rates to these loading frequencies. So earthquakes are somewhere here, and this is really getting into the shock loading rates. So if you look at the response of the material, this is again superelastic, you can see here, the loops are quite stable and they go up to 7% strain without any problems. Then what we did is we increased, once the material survived the 7% strain cycles, we increased the strains to up to, in this case, 12%. There was some shifting of the hysteresis loops, so if you increase the frequency, basically everything moves up. But again, very stable hysteresis loops. We didn't see any fracture in these tests. One of the bars, actually I think the same bar, we pulled it to failure. As you can see here, there was an extensometer on the bar, and we measured the strains through the extensometer, not based on the actuator displacements. What we have seen is this material can really go up to 25% strain, which is very similar to a mild steel. The other thing that we looked at is the temperature dependency of this superelastic behavior. So this was a quasi-static test, so we wanted to obviously exclude the effect of the strain rate. This was done under quasi-static loading. We tried here 5 different temperatures from minus 40 C to all the way up to 50 C. As you can see in this graph here, there's quite a dependency on the temperature of the superelastic behavior. Under normal conditions, room temperature is about 25, let's say, you see this behavior of about 250 MPa yield strain, and then if you increase, you go up, and if you decrease the temperature, you go down. At minus 40 C, which is not uncommon, I mean, you can see minus 40 in some parts of the US, the yield strains go really down to 100 MPAs, which is a concern, which we're still debating how we could address that. But the nice thing, at least, is the material still shows the superelastic behavior. It doesn't rupture or does anything weird. That's all about the materials. Now I would like to start talking about these columns. So these are the columns that we built and tested. So these are 8-inch diameter columns, and they have about 2% longitudinal reinforcement, about 0.6% transverse reinforcement there. The aspect ratio is 4.5, so the loading point is about 36 inches from the base. These are pretty small columns. You will see some pictures later on. So this was the conventional reinforced concrete column. This is the ECC tube. So you see on the outside we have ECC. This is 1.5 inches wall thickness, and then inside we fill with concrete. And then this is the detailing for the SMA in the plastic hinge region. We have a 3/8 diameter SEA bar, and these are coupled to regular steel, mild steel rebar through some threaded couplers. Now, these are the ECC designs. This is the conventional concrete with a target strength of 35 MPa. And then we had 2 ECC designs. These are very common designs from literature. The only difference between the 2 designs is the amount of fly ash. This has twice the amount of cement. This one has 1.2 times the amount of cement. And they both have 2% by volume of PVA, polyvinyl alcohol fibers, in the mixture. Now, we tested 6 columns. So the first column, these are the cross-sections here at the plastic hinge region. AA is the cross-section in the plastic hinge region. BB is the cross-section above the plastic hinge region. This is the conventional concrete column. So the black circles here are the number 3 bars, if you like, and the blue ones are the number 4 bars. On the neutral axis, these are tested in uniaxial bending. So these blue bars, or if you want to cut it vertically, that's where the neutral axis is. And then In this case, this is very similar to a conventional column. The only difference is that instead of putting concrete, we put HFA, which is one type of the ECC we are looking at. And in this case, this is now the tube, but still has the steel reinforcement, so there's no super elastic alloys in this one. And then this one is the same as the previous one, but it uses a different ECC. Instead of using HFA mix, it uses M45 mix. HFA has high fly ash, that's why it's called HFA, and M45 has a little bit less fly ash. And this is the HFA tube with SEA bars. So we have 6 bars, so 3 on each side of the neutral axis. And now in this case, we coupled these bars, the SEA bars, to a number 4 bar, although we had number 3 here, because we wanted to make sure that if you use similar diameter bars, you want to make sure that the SEA bars will yield before the steel. That's the point. And in this case, we only used 1 on each side of the neutral axis, and the other 2 were regular steel, so number 3 steel bars. So this is how we constructed these specimens. These are kind of small, so it was a little bit tedious to construct these. So you see on the upper left here is the SEA bars with the couplers connected to the steel. Here we put a tube inside this cage, so that it serves as like the inside formwork, and we put the spiral reinforcement around it, and then we had an exterior formwork. We poured the ECC in between the two. ECC is almost self-consolidating. It doesn't require really any vibration, so you just pour it inside the gap, and then you get this tube here. And then we put this tube inside the foundation. We assembled the formwork on top of it, and then we poured concrete in the foundation. We filled the tube. And then this is after we removed the formwork, and then we cleaned it up. We cut these PVC tubes and so on. And then this is what we get eventually. We use what we call the LBCBs. Those are multi-axial loading units. So you see this yellowish platform here. It can move in all 6 degrees of freedom. And we can control forces and displacements independently. So we can do mixed mode control, like we can control the axial loading in force while the horizontal movement in displacement. So that's what we call the mixed mode control. And in this test, we used about 22.5 kips of axial loading, which corresponds to 100 kilonewtons. And this corresponds to 7.5% of the gross axial capacity of the columns. And this was our lateral loading protocol. We started, I think, about 0.5% or 0.25% drift. And then we applied 2 cycles at each drift level, and we went all the way up to 10%. Before I move on and show you the results from the column testing, I would like to show you some of the material tests we have done. So since I mentioned that these bars are not so robust like the nickel titanium ones, we wanted to make sure that they will not rupture. Some of them had some premature rupture, so you just take the material, you just load it very slight, like 1%, 2% strain, it ruptures. So to make sure that these are not those bad ones, so what we did, we tested each and every bar that we put inside the columns. So this one is one of those, like this one here in this case, this bar here. This is what we call the training. So we train them to be nice and kind to us when we do the column testing. And this was another one of those, and this was another one of those, and so on and so forth. So they were very similar in terms of the strains and stresses. Stress-strain response was very similar. There wasn't that much of a variation, but again, some of the bars ruptured prematurely, so we wanted to make sure that they're okay before we put them in the columns. And then if we want to compare this to one of the steel we used, in this case, this is the red one is the steel response, and the blue one is the copper-based SCA. So as you can see, there's a significant difference in terms of the initial modulus, and there's a significant difference in terms of the yield strength. Yield strength, we are not too much concerned about it because we want the yielding to be there already, so we want to reduce the yield strength there, the yield strength of the bars there, but the modulus might be an issue depending on the situation. So these are all the things that we hopefully will address later on in the research. So this is the ECC behavior in uniaxial tension. Testing any cementitious materials in tension is tricky because they're very brittle. Even if they go up to 3-4%, you need to make sure that you're really applying uniaxial loading rather than bending or torsion or anything. So we came up with this design that was basically releasing all the other degrees of freedom so that we end up with only the axial degree of freedom. You can see this, we release all the, we are missing one plate here so that we can show you the specimen here. And then we made this just a uniaxial test. These are the results that we got from the larger batches of ECC. If you prepare small lab mixes, it's much easier to control the strains. But if you want to make really structural scale mixes more than, I would say, 3-4 cubic feet, then it's very difficult to control the properties of ECC. And this is also documented in the literature. So what we got for these columns wasn't what you would maybe commonly see in literature for ECC. We got about 0.5% strain. This is still like 500 times more than what you see in concrete, but 550. 50 times more than what you would see in concrete. But still, it's not as high as we would expect. So we're working on it to see how we can make ECC go to higher ultimate strains when we produce it at a larger scale. Now, this is the image evolution of the specimens with drift. So you see the 6 columns we tested here, starting from the reinforced concrete. This is the HFA solid section. This is tube plus concrete inside. Again, these two are 2 different ECC mixes with the same reinforcement, steel reinforcement. This one with 6 SEA bars, this one with 2 SEA bars. These both have the HFA mix. And this on the right is the drift level, and these are the cracks on the columns. You saw the largest distribution of cracks in the HFA tube, and no spalling in any of the ECC columns. So none of these ECC columns we have seen spalling. The reinforced concrete columns started to spall around 5% drift. And as you can see here, we have significant spalling of the column, and there was some rebar buckling in the reinforced concrete column. So what happens in these 2 columns with the SEA bars is really there is one large crack that opens and closes because there's the really weak cross-section there. You have the maximum moment, and then you end up opening up the section, and then it goes more like a rocking type of motion there. So this is eventually at 9.5% drift. This is what we got in terms of the crack distribution and damage. These are the hysteresis loops for all 6 columns here. So as we go from here, you see these are stable hysteresis loops for all of these columns. Then the nice thing that we have seen is if you look at this HFA column and HFA tube, their response is almost identical. So whether you make the entire cross-section HFA or you just make a tube and fill it with concrete, the response is very similar. We see a very little difference in the strength and everything else. I'm going to show you that later on quantitatively. And then the same thing here, M45 and HFA tube, they were very similar response. I mean, the material behavior was also very similar. So adding more fly ash, if you want to use more fly ash, doesn't really hurt. Actually, it helps a little bit. And then this is the HFA tube with 6 SCE bars. You can see that the permanent drifts, which you can quantify as this 0 force crossing point, is almost 0. Basically, all the hysteresis loops, when you unload, they cross through the origin. You end up with almost 0 permanent drifts. But we have seen some rupture of the SCA bars at large strains, large drift levels. This was about 7%, I guess. And then there was another, so these 2 bars ruptured. These are very high drift levels, but still there was some rupture of the SCA bars. In this case, this one ruptured about 5% drift. Now, in order to make a quantitative assessment of these different designs, we found these envelope curves in the push and pull directions, and then we averaged those 2. So these are the 2 on top of each other, and we averaged the 2. And then we took that average envelope curve and found the yield point. So we looked at the yield drift and the yield force, and then we found the maximum point, maximum force, and the corresponding drift. And then we defined the ultimate point to be as the 15% reduction in the load level. And then we defined 2 more metrics. One was the permanent drift, which is this point where you cross 0 force as you unload from the 7% drift cycle. And the energy absorption we defined as the area inside these hysteresis loops. So we looked at one of the things that this was also commented on in the previous presentations. The yield drift increases at anywhere from 32% to 68% in this case when you use ECC. Just ECC, there is no SCA. And then the yield force, the increase is about 15% with ECC. These obviously show you lower yield forces because of the presence of the lower strength bars. And then the drift at max is also, again, it's increasing even without any SCA bars. And then maximum force is about 15% higher. The drift at ultimate is very similar. In these cases, it's actually lower because of the rupture of the SCA bars. And the ultimate force is the force at the ultimate point here, 15% reduction from the max. These 2 are very interesting. I want to spend a little bit more time on those. The permanent drift is this point here. Upon loading from 7% drift, we see about 91% reduction in the permanent drift when we use 6 bars. The permanent drift is almost nothing, 0.3%. And in comparison to 4.25% drift in the case of concrete column. And the energy absorption is significantly less, obviously, because you don't have that yielding of the bars, nice fat hysteresis loops. We see a significantly lower energy dissipation in these 2. But if you want to dissipate more energy, you can there's always a compromise between this permanent drift and the energy absorption. If you want to put more steel bars, you will get more energy absorption, but also more permanent drift. So this is really 2 competing objectives here. So these are the plots for the permanent drift versus the drift at the top of the column, and then the energy absorption, again, plotted against drift. You see that this column here with 6 bars it has almost zero, very low permanent drifts. And this one, which is with 2 bars, it has significant reduction in drift as well. And energy absorption is also proportional. If you put more bars, you get less energy absorption. If you put less bars, you get more energy absorption. These 3 were quite similar to each other. The RC column and the HFA columns with the tube, with the steel bars, were very similar to each other. I'm going to skip these. This is just a recap of what I just told you. So what we want to do in the future is, one of the things is to improve the behavior of these copper, aluminum, manganese bars. We're going to work with this Copper Alliance. They're very interested in this material, so we're going to work with them hopefully to make this material commercially available for construction industry. And then we want to do some multifunctional material of design of ECC. We want to do some combined durability and mechanical performance tests at the structural scale. What we have been doing up to now has been only the seismic loading, the mechanical loading. Now we want to age some of these columns and then subject them to some seismic loading. We need to do some modeling of this to better understand what's going on, and then we're going to also do some probabilistic life cycle assessment. I think that's about it. Thank you so much.